Hi, this is Nick Pizzi, and this video is part of the Applied Math series for water plant operators. Practical math that we're using the Lake County, Ohio Aquarius water treatment plant for our reference. So let me share that video with you shortly here. So this is practical math for water treatment plant operators. It's the fourth in our series of license exam training modules for water plant operators. And we're basing that again on the Lake County, Ohio Aquarius water treatment plant. If you want to see more videos in this series, at the end of this video, there will be a link that you can click on and bring you to it. For all of these videos that we're making in this series, we include these couple of tables that you can use as a reference to work the math problems that are embedded in here. This table is a conversion table from going from English units or American units to metric units. For example, if I wanted to change kilograms to pounds, I would multiply by 2.2046. And whereas if I wanted to go to pounds to kilograms, I'd multiply by 0.45359. So this table just helps you go back and forth here. And this second table is some information that we've included in general, but also some things that are specific to this exam that we're going to give you. For example, if you look in the second column, it says atomic weights of some elements. You're going to need those to work some of the problems. We've given you the formula for phosphoric acid. We've given you the formula for hydrofluorosilicic acid. Then in the next column, we tell you that hypochlorite is 1 pound per gallon is a 12% solution, 1 pound per gallon chlorine. A 6% solution is a ½ pound per gallon chlorine. 15% is 1.25. So hopefully you get the point that this is a linear progression. But you should be able to draw yourself a little graph to determine how to work some of these problems that are going to come up. We tell you some information about in the last column about the Aquarius plant itself, about its sedimentation basins and its weirs. So you'll need to dig that information out also. We've included in this one a monthly report for March that the Aquarius plant put out that lists some of the chemicals that they've used, the water treated. Gives you a little bit of information in the notes in the bottom row there that tells you some things about some of the chemicals. So you'll have to dig some of this information out also. This is pumpage, pounds used, gallons used, that sort of thing. So with that, we're going to go to the first math question, which is this. Question number 1 says, the Aquarius plant has 4 rectangular sedimentation basins. We've covered that a few times before, and we've also mentioned that the plant has a treatment capacity nominally of 20 mgd. So if that's taking place, 4 basins in service, 20 mgd rate, what is the detention time in hours and minutes with all basins in service? And of course, this is a detention time problem, always equals the volume divided by the flow rate. So what I've done is taken the flow rate of 20 mgd, multiplied it by 694, and I come up with a working flow rate of 13,880 gallons per minute. Of course, if you want to pause the video at this point, go ahead and do so to work the rest of the problem. I'm going to continue working here. So I've got the flow rate down. Next, I'm going to go into the table. I'm finding that the basins are listed as 41 feet wide, 190 feet long, and have a water depth of 14.5 feet. So on your exams, when you see W.D. that means water depth. It's how deep the basin is. They're listed as 14.5 feet. So now we have the 3 dimensions of the basins, and we know that there are 4 of them. But we can determine a volume. And we know the detention time equals the volume divided by the flow rate. So we can get that volume worked out here. And I've got that listed as 41 feet by 190 feet by 14.5 feet deep times 4 units. And then I multiplied by 7.48 gallons per cubic foot. So change those to gallons, and I divide it by the gallon per minute rate. I come up with about 243 minutes, or about 4.01 hours. Hope we did well on that. Let's move on to question number 2. Question number 2 asks, it tells you that the regulators say that said basins should be designed with a longitudinal flow through velocity no greater than 0.5 feet per minute. A longitudinal flow would mean the plane would be the width of the basin times the depth of the basin. So that rectangular unit that is cut out by the width and the depth, think of it as flowing through the basin this way. How fast is that thing moving, basically, is what they're asking you to do. They're asking you, what is the flow rate in velocity, flow through velocity at the Aquarius plant at that max flow? We know that was 20 mgd, and all the basins in service. So you would have to dig out that information and work it out. If you want to work this one, pause the video now, try to work through it with pencil and paper, get your calculator out and come back and try this again. I'm going to move on. I took the 20 MGD rate and I converted it to cubic feet per second, because I know that if I multiply by 1.55, I'll go from 20 mg, I'll go from MGD to cubic feet per second. So this comes out to 31 cubic feet per second. If I divide that by 4 basins and I convert it to minutes by multiplying by 60 seconds per minute, I'm figuring that there are 465 cubic feet per minute per basin. So now I can set up my problem V equal Q over A. I'm going to set up the 465 cubic feet per minute, and each basin is 41 feet by 14.5 feet. And I come up with 0.78 feet per minute as a flow through velocity. I've got a little asterisk here because I want to explain something to you. Again, this plant was built in 1980, or put online in 1985. It was built the year before that. I dug up the original O&M manual that was put out by the design firm that created this plant. And in 1985, they put in there that they had calculated a flow-through velocity of 0.79. So there's close agreement between what I calculate and what they calculated all those years ago, basically the same number. But in the question, I mentioned that the regulators, typically Ohio EPA, which might go by 10 state standards in this case, call for nothing greater than a 0.5 feet per minute. So I don't know why that is. I don't know how they were able to do that back then, whether that requirement was even on the books back then. But certainly these operators at Aquarius know that if they have a basin out of service, for example, and if they're a high flow rate, they've got a pretty aggressive flow through velocity that they got to be very careful about. So that's a good piece of information for them to know. All right, let's go to question number 3. Question number 3 asks, what is the average surface overflow rate for sedimentation in March, assuming all basins were in service? What was the surface overflow rate on the max day? You can see I accidentally brought them up too quickly here. But this is a standard surface overflow rate problem that requires you to go in and dig out information. If I go back to the March report, it says that the water treatment plant treated 232.2 million gallons in 31 days, because that's how many days in March, or the average of 7.49 MGD. And that number is in the table too. Also in the table is the max day for the report was 12.35 MGD. So now I've got the average day and the max day in MGD, which I can convert to gallons per minute and divide by the square foot area of a basin to come up with my surface overflow rates. And you remember in the previous video that we put out, we like to be no greater than 0.5 gallon per minute per square foot. And you can see that these two rates work out pretty conservatively. I take the 7.49 MGD, convert it to gallon per minute. Did the same thing with the 12.35 MGD, converted that to gallons per minute. And I did my calculations. I took the basins, 4 of them at 41 by 190 or 7,790 square foot each. And I did my surface overflow rates that way. The 0.167 and 0.275, very conservative rates. Now, this is a little bit more difficult. This one actually took me 4 pages to work out. So if you want to work this one, you'll be stopping the video after I read this information to you. The phosphates are used at an Aquarius plant for the lead and copper compliance program. So they use phosphoric acid. How many milliliters per minute of phosphate, not phosphoric acid, but phosphate, was put into the water using 30% strength phosphoric acid on average in March? So let's think about that question, the way they're asking it. We know that Aquarius plant has phosphoric acid. They don't have phosphate that they put in the water. They have phosphoric acid that they put in the water, part of which is phosphate. Now, this is one of those dosage problems that has to work with a couple of percentages. We've got to know that the strength of the acid, in this case, was 30%. Not all of the acid is phosphoric acid, only 30% of it. The rest of it is just water. So we have to use that percentage in our calculations. But also, we've got to dig out the formula, the formula, chemical formula for phosphoric acid, which I find in the table, and realize that only part of that chemical formula is PO4. Some of it is hydrogen that I'm not going to use in my calculation. I got to figure that percentage too. When I go into the table, I see that phosphoric acid is depicted by the formula H3PO4. And as stated, it's 30% strength. So if you look at the amount of phosphate in the molecules derived by adding the atomic weights of each element present to get a total. I'm going to get the total formula weight by seeing that there are 3 H's, and H is a 1 for atomic weight, so 3 times 1 is 3. So that's the contribution of hydrogen. In the phosphate, similarly, there's 1 P. The 1 times the formula weight of phosphorus is 31 equals 1 times 31 equals 31. And that there are 4 oxygens. And oxygen is listed as 16 in the table. So that would be 4 times 16 or 64. So the total is 98, but not all of that 98 is PO4. I just take the weight of PO4 divided by the H3PO4, and that comes out to a percent of phosphate. When I work it through, it's 95 divided by 98, or 97%. So that means that 90% of the phosphoric acid molecule is available as PO4. So now we've learned 2 things, 2 percentages. Of the phosphoric acid that I'm putting in, only 30% of it is the acid. And of the acid, only 97% of it is PO4. So I've got to use those 2 when I do my dosage calculations. However much phosphoric acid is used, and this is another way to look at it, no matter how much I use, 97% of it is the needed PO4 and 30% of it is the acid. So I use those 2 calculations. Here's question number 4 continued. Oops. So we need to use the strength and density of the acid that was shipped to the plant. And as we mentioned in the question, it was 30%. Now that can change from load to load. So whenever you get a load of phosphoric acid in, you always got to check the bill of lading to see what percentage it is. These guys have a contract, it brings them to 30%. So the specific gravity of the product was shown in table as 1.575. And so the pounds per gallon that this material weighs is 1.575 times 8.34, or 13.136 pounds per gallon of phosphoric acid, not phosphate, not P, not anything else. Phosphoric acid weighs, in this particular case, 13.136 pounds per gallon. So, the March report states that the Aquarius plant uses an average of 130.1 pounds per day phosphoric acid. Well, we don't have pounds, we have gallons, so we got to work that in. 130.1 pounds per day, multiplied by the fact that 1 gallon weighs 13.136 pounds, I come out with a calculation of 9.9 gallons per day of phosphoric acid used. Now I know that not all of that is phosphate. I've already figured out that it's 30% and 97%. I'm going to work that in there. The 9.9 gallons per day divided by 1440 will give me gallons per minute, times the 3,785 milliliters per gallon will give me milliliters per minute phosphoric acid used. That's 26. So 26 milliliters per minute is the dose of phosphoric acid being put into the water here to treat it at Aquarius plant. And of that 26 milliliters per minute, only 30% of 97% of it is actual phosphate. I'll work that math out. 30% is 97%. I'm coming up with 7.56 milliliters per minute phosphate going into the water. Now they asked another question, so we'll continue with that. So the average doses of phosphate in the water can be calculated as follows. Milligrams per liter equals 138.1 pounds per day divided by the flow rate of 7.49 million gallons per day. I'm coming up with 18.5 pounds per million gallons phosphoric acid. I take that 18.5 pounds per million gallons divided by the 8.34, and I see I get a dosage of 2.2 milligrams per liter acid. And we know that only part of that is the phosphate that we're looking for, and that was the question. I'm going to take the 2.2, divide it, multiply it by 30, multiply it by 97%, and coming up with a dosage of 0.64 milligrams per liter PO4. Hope you got that right. Let's move on to question 5. Question 5 is similar. It's going to use the fluoride instead of the phosphate. Fluoride is another molecule. Fluoride is another treatment chemical, I should say. It comes from a molecule, part of which is fluoride, and part of which is acid. So we got to figure those 2 percentages just like we did with the phosphoric acid. So we're here in Ohio, and of course we got to comply with Ohio regulations, which require us to keep fluoride in the water, somewhere between 0.7 and 1.3, I believe it is now. Fluoride is put in the water to help prevent dental caries, of course. And the question is, how many milliliters per minute of fluoride ion was put into the water on average in March? What dosage of fluoride ion is this? So we go back into the tables. dig out this information. We see that we use 26.6 gallons of F acid per day. I'm going to multiply that by 3,785 milliliters per gallon and divide by 1,440 minutes. And I see that I use 69.9 milliliters per minute. Sorry about that decimal point there. So if the F acid fed is 26.6 gallons per day, and I divide by the million gallons per day, I'll come up with a dosage of 3.55 gallons of fluoride acid per million gallons. Of course, not all of that is fluoride, only part of it is. So I've got to work those equations also. So the 3.55 gallons of fluoride acid per million gallons divided by the 1.2 and the 8.34 equals 3.55 gallons divided by 10 gallons, or 35.5 pounds of fluoride acid per million gallons. So the 35.5 pounds of fluoride acid per million gallons divided by the 8.34 is going to give me a dosage of 4.2 milligrams per liter H2SiF6. Now that 4.2 milligrams per liter of H2SiF6 was only part fluoride. And you can see the formula there, so we had to dig out that information. When I work those through using the formula weights, I come up with a 79%. We also see from the table that the acid was 24.4% strength. When I multiply all those times the 4.2, I come up with 0.81 milligrams per liter fluoride ion. Hope you did well on that. I think we have one last question here. What's the average dose of chlorine in milligrams per liter if the hypochlorite solution is 14.3%? Okay, so we gave you something in the table that showed you that if it's 12%, it's 1 pound per gallon chlorine. If it's 6%, it's a half a gallon per minute chlorine, half a gallon per pound, half a pound of chlorine per gallon. So we got a linear equation that we can follow here, a linear progression, I should say. So from the table, we see that we use 138 gallons per day of hypo solution. And if it's 12% is 1 pound per gallon, I've got 14.4%. So I set up this equation. I set up a proportion equation. The way I do it is this. I put X pounds of chlorine per gallon is to 14.4% as 1 pound chlorine per gallon is to 12%, because that's what they gave me. So when I work for X, I see that a 14.3% solution of chlorine is going to give me 1.2 pounds per gallon of chlorine. Now the 1.2 pounds of chlorine per gallon times 138 gallons is going to give me 165.6 pounds of chlorine being fed in the day. Divide that by the million gallons, I come up with 22.1 pounds of chlorine per million gallons, and divide by 8.34, and I get a dosage of 2.65 milligrams per liter chlorine. Hope you did that fine. Got that done well. Those are good problems that are going to show up on exams where we have to use the 2 percentages in our calculation, so you need to get used to those. So once again, we want to say thanks to the Lake County Department of Utilities for letting us use their data from the Aquarius plant. This is part of an applied or practical math operator series, and you'll see some material come up here that you can click on if you want to either subscribe to this channel or follow on to the next video. So with that, we're going to stop sharing, and thank you for your attention. Hope you did well.